In today's video, we'll take a look at yet another gradient descent based optimization technique, which this time is called root mean square propagation. It's an unpublished adaptive learning rate method that was proposed by Jeff Hinton in his Coursera class on deep learning. So the link will be in the description if you're interested in that. So the main goal of this algorithm was to resolve AdaGrad main problem with the vanishing learning rate. If you want to learn more about AdaGrad, how the algorithm works, you can take a look at the linked video in the description. Right, so let's look at the formula for root mean square propagation. So if you're familiar with gradient-based technique, there is nothing very outlandish about this formula, but we're going to unpack it nonetheless. So it looks very similar to AdaGrad, except that we have a running mean in the divisor over here, the e, the expectation of gradient exponent 2. So if we look at this part, the weight update, we have the following terms. We have theta t, which is the current weight at time t. This is a vector. We have theta t plus 1, which is the updated weight. So this is what we're trying to calculate. We have n, which is the learning rate, which is usually set to 0.001 for deep learning models. We have a gt, which is the gradient calculated at time t. This is also a vector. Epsilon over here is the parameter we add for the numerical stability, so just to avoid a division by 0. The expectation over here of g2 is the running mean and is defined as follows. So this is the formula of this thing. Here we have 0.9, which is the decay factor, which in turn suggested to put at 0.9. We have the expectation g2 at t minus 1. This is the previous running mean value, right? So this will change. At the beginning, this was set to 0. So we only look at 0.1 times the gradient. We'll see that. 0.1 is 1 minus decay factor. And finally, gt exponent 2 is the gradient vector exponent 2. That's pretty much it. There's not much to it. Let's now look at the Python implementation. And the code is available on the GitHub, which is linked in the description. Alright, so here's the Jupyter notebook. In this notebook, there's multiple optimization technique all at once, but we're going to focus on our RMSProp. How we're going to test if our algorithm work. We're going to use the simple dummy linear function that we're trying to learn because it's easier to set up. It's just a sanity check to see if we can learn anything, if the algorithm is just working well. I'm going to run into some setup, and after that I'm going to show you the RMSProp. If you want to look at the other stuff, you can you're welcome to open the notebook yourself. So this is the model that we're going to define. It's a line model. It's this thing. We have the bias plus the slope. This is the bias, this is the slope, and this is just a random initialization. Evaluate is how we get y hat, so the current estimate, right? Dx at w0 is the partial derivative for w0, and dx w1 is the partial derivative at w1, and we just literally calculate that by n. This is for pretty printing, and the last thing that is important is this. So just a way to sample stochastically the data vector. So we have xs and ys, and we're just doing permutation and taking one number. So that's pretty much what we need. This is gradient descent. This is stochastic gradient descent. We have with momentum. We have AdaGrad over here. You're gonna see the structure of RMSProp look pretty much like this, except those gonna be changed by e. Let's take a look at it. So we have the model, which is a line model. We have xs and ys, which are the data. We have the learning rate, which is set to that, the decay factor at 0.9, and max number iteration, and finally the epsilon over here for numerical stability. You can read that if you want. I'm going to run into the code, and then we're going to take a look at the test. So the first thing we do is we set the e, the running average, to 0 for both w0 and w1, and we iterate for as long as there are iterations. So the second thing we do is we take a sample, right? So stochastically take a x and a y that are matching. So this is the stochastic gradient descent part. We calculate the gradient, right, using the thing that we saw before. So partial derivative of w0 and partial derivative of w1 at this x and at this y. And then we use those things in the calculation of our new running average for this part. So we have the decay factor, which is 0.9, and this is 0.1, and this is the previous running average, and this is the gradient exponent 2. There are some refactoring to do here, but this is, I unpacked it just so that it's easy to show. And this is the update, so it's theta at t minus the learning rate n divided by the square root of the running average plus the epsilon times the gradient. And that's it. That's how we update the thing. So let's actually run this. So here we have x and a y, which should give us an intercept of 0 and a slope of 1. It's obvious why. Let's take a look at all of them. There's a lot of, let's just look at the RMSProp. So we should get 0 plus 1x. And that's what we get. We get, wait, where am I? Yeah, this is 0 and 2. Sorry, I messed up. So we should get 0 and 2, which is what we get. I think 0 and 1 was above. Yeah, it's this one. So let's take a look at that. We have 0 and 1 for Allegrad. I did a lot of iteration, but honestly, this is not... It converged way before. But just do it for demonstration purposes. So this one, 0 and 2, we saw that it was good, and this is obviously an intercept of 0 and a slope of 2. Finally, if we look at an intercept of 1 and a slope of 2, this thing doesn't work because of these guys. Sorry, just rename these. GD. And let's go. So we should get 1 and 2. And we got that. So it's basically 1 and basically 2. So that's it. There's not much to the algorithm. It's just the concept that make more sense. But these algorithms are usually used for deep learning model. But this is just to show you what the code actually look like. Alright, that's it for today. I hope that this tutorial was useful. If you have comments or questions, you can leave them down in the comment section, and have a great week.